Hello, this is Jeremy Comel and welcome to LipidMatch tutorial part 6. In this tutorial we'll first go over how you can modify which fragments are needed for conformation for a given lipid. We'll then, for advanced users, go over how to develop your own lipid libraries to integrate with LipidMatch. So let's start. If we go into our LipidMatch folder, we can select the LipidMatch libraries. You'll find that within the LipidMatch libraries, if you scroll, you find in all caps locks is this lipid ID criteria. Don't move this. Keep this in the library. But you can open and modify this one. I suggest that you make a copy of these libraries so that you don't edit the original libraries in case you make a mistake. So here in the copied version, we'll look at our lipid ID criteria. So now you can see for each lipid there's a CSV file, and then it shows the CSV file that needs to be imported for that lipid, and then there's a columns that all those fragments need for conformation, and then a column where at least one of those fragments are needed for conformation. So let's take a look at, for example, and here I like to do view freeze panes. Let's take a look at phosphatidylcholine. Now let's look at the negative CHO2. So in this case, the end column is saying that it needs to observe both column 10 and 11 within the libraries. So what does that mean? That means if we open up LipidMatch libraries and we go to PC, we open it up, that means that column 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 are needed. So it needs to see both of these fatty acyl negative ions for conformation. That's what it's saying. Now what happens if you have something where there's one or the other fragment must be observed? So if we look at, for example, the PE protonated, we see that column 3 must have a fragment identified, and column 4 and 5, either of those columns, at least one of them has to have an identification of the fragment. So again, if we look at our lipid libraries and we look at the protonated PE, can open it up. So 2, 3. Okay, so you need to see the neutral loss, which makes sense. It's the dominant fragment ion. That's why we chose it. And then you have to see a neutral loss of either one or the other tails as RCO+. So if you see a neutral loss of either of these ones, then it's a confirmed lipid. Now on our right, you can see some of the definitions of those lipids, how their acronyms are defined. You can also do things such as sort by the adduct or the polarity, or whether it's run by class only or just by fatty acyl chains. So for example, let's sort it by the CSV file, which is the default, and that way you can scroll through in alphabetical order looking for your lipid class. So you could change one of these. For example, let's say I look at that PE and I want to be more confident. I know the neutral losses are low abundance, so I'll get less identifications. But I want to be more confident in my identifications. So I decide that, hey, I have to see the neutral loss and of both fatty acyl chains as well as the head group. And I have to see all three of those ions for confirmation. Then I would save this and make sure I select the library when I'm running LipidMatch that has this new saved lipid ID criteria. So that's how you'd modify the identification criteria. Now, what if we want to generate our own lipid MSMS libraries? The first thing you're going to want to do is you're going to want to find example exact mass fragmentation for at least 2 species from that lipid class you're interested in. And you can use that now to generate all of the other species fragmentation, and I'll show you how. First, if you go into your LipidMatch folder and you go into Additional Tools, Fatty Acid Chains, here you can generate the combinations of any 2 fatty acid chains. There's already some example inputs here. So here's common fatty acids. So we're going to use this and generate all the combinations for a lipid containing 2 fatty acyl chains of these lipids. Just for fun, let's say we wanted to add another lipid to this, another fatty acid that we thought might occur. We can add 19:1, and then of course we'd have to subtract the mass of 2 hydrogens. So we can look up the exact mass of hydrogen. I like to use this exact isotope mass calculator. So we can go to high resolution. You can pause and take that link down if you want. Hydrogen, which is 1.00783. So I'll copy that. I'll say minus 2 times the exact mass of hydrogen. Now we have 19:1 as well. So now we have our list of fragments. I'm going to save this. And now we can generate the combinations. You can either use the same fatty acids or different. So for example, let's say I wanted to use a D, like D18-1 for sphingomyelin. So there's only a few of those fatty acids and I wanted to combine them with a different list of fatty acids. Then I would use this different fatty acid combine. The same fatty acid combine is assuming that you're using the same list and just taking the combinations of it. So again, you open the script in RStudio, select everything, and click Run. If the pop-up doesn't appear, that means it's behind some of your windows. So again, I'm not going to install the new version of R, but it's suggested that you do. Now I select the list of fatty acids, and you saw the format, so make sure the format's the same. And then the output directory, let's say our desktop, and then you can see how quickly that code runs. And now you have the combinations of all the different fatty acyl chains, which you can use to generate a library. So let's generate our library. We're going to insert another row here. And here we're going to have the name of the lipid class. Let's say we're going to do PC. So the PC is the lipid class, what we want to call the lipid class, the acronym for it. And then you're going to have the different fragments. So first you start with your adduct for the precursor, and always have these 2 columns in that order. So let's say I want to do N plus H. Then you can do a number of other fragments. So if we look at our example lipids, we have the loss of the head group, the loss of 2 fatty acid chains, and the head group. So let's add those. Now how do we calculate these? First thing we do is we want to know what's the difference between the fatty acyl chains and the entire precursor mass. So I'm going to find 16:0 and 18:1. 16:0 being 255 and 18:1 being 281. So now I can do a mathematical formula, and I'll take the precursor mass minus these two fatty acyl chains should give me the backbone mass or something. This number, whether it's the exact backbone mass or not, is what you would add to the two fatty acid tails to get back to the precursor mass. So I can show you, for example, if I added the two fatty acid masses plus that quote-unquote backbone mass, I should get back to my original ion mass to charge. So we do that now as a general formula. So if I go over here to PC and I want to create the M plus H mass, then let's copy this and paste special as just a value. So now I can copy this mass. I'd say the precursor mass is the tails plus the backbone mass. So here we can double click and it will fill down. So if we were to look at 16.0.18.1, scrolling down, we see here 16.0.18.1, 760.5851. So that's a verification. I use the second lipid that we've got information for a verification at the very end once I find all the fragments to make sure that they're correct. The more verifications you have, the better, of course. So now for the neutral loss of the head group, that's easy enough. We know now that it would be the difference of the precursor minus some kind of neutral loss will give you the neutral loss. So that ends up being 183. So again, we can paste special values. Now we can use this number, so we all just say whatever the precursor is minus 183 gives you the neutral loss of the head group. And again, at this bottom edge of the corner, double click, and that will fill down. So now you have a neutral loss. So any neutral loss, you take whatever the ion is in which the neutral loss occurs from, usually the precursor, and subtract that neutral loss mass, and then you can just scroll down. Now it's very similar with the neutral loss of the fatty acid chains. So in this case, for the neutral loss of the fatty acid chains, it's the precursor minus whatever that fatty acid chain would be. So tail 1 is going to be 16:0, 255, right? And then that gives you 505. So you can see that the difference is there's one more hydrogen based on this neutral loss. So maybe our tails are RCOO, and the neutral loss is RCOOH, something of that nature. So I'd take the mass here and subtract. Again, I get the mass of hydrogen. So we can copy this. It's going to be an addition, right? So we got 505. We should have one less hydrogen in the actual mass. So we'll take the precursor and subtract the first fatty acid, and also now subtract one hydrogen. It's already a subtraction. Now we can double click, scroll down, and that will populate. So we'll do the same thing for MH minus tail 2. I'm going to drag this over. Now you can see that it's grabbing from the MH minus PC group. We want it to be the precursor. And we want the other value to be the fatty acid from the second chain. So there we go. We can scroll down. Now we can verify again, looking for 16.0.18.1. And here's 16.0.18.1, and you get 504 and 478, indeed 504 and 478. So it's working thus far. Now we get the PC head group. So anything which is just an ion not a neutral loss, is going to retain that same ion. So I want to copy that, paste it here. Notice that if I drag down right away, sometimes you'll just get 184, but other times it will start adding 1 every time. So you want to be sure that this mass stays the same as you click the edge of this box and fill down. So we've completed now our library, except for we need to create the names. So in the case of creating the names, we use a concatenate function. Concatenate. So equals concatenate, open bracket, put the class in another open bracket. Actually, open brackets already exist here. So PC, comma, and then that first fatty acid tail, underscore, because we don't know the order of the fatty acid chains based on mass spectrometry. And then we also want to include the second fatty acid, and then close parentheses, and then plus whatever the ion is, so in this case plus H. And I'll close that. And so here we get the lipid name. I don't want this first parentheses, open parentheses, so I want to replace that. The problem being, if I replace it, it will convert it to a time, which you can find out yourself. So I'm going to replace it with an underscore. Notice here that added an underscore here, so we don't need any more of the underscore. So if I was to reiterate what just happened, we see that here you have 8:0, open parentheses, and so we're pasting these things together. So in the concatenate function, we add a PC as the name, then we paste together with the open 8:0, paste that to the underscore 8:0, and then add a close parentheses plus H. That should give us our name. Again, drag down the function. Now you have all your lipid names, the precursor masses, all the fragment masses. Make sure you put the adduct here for the precursor mass because it's used in the software. Make sure you put the class here as the title for the first column. Now once you have that, select that, Control C, paste it into a new Excel sheet just as values. You can save the other workbook if you want all your calculations for later. So now we have our library. You can go to File, Save As, and then you can add it to LipidMatch libraries. PC, H, let's call it with 19.1, right? Because we added the 19.1. So if we look down, we can see now that they all have the 19.1 as well. Now, we can close all of these. After, if you want, you can save them. And we'll have to add one last step. So let's go to our LipidMatch folder. Our LipidMatch library is modified. Lipid ID criteria. And we're going to add a new row. So let's do, or we can start from the bottom. So for the CSV file, we have to put the exact same name, which should be contained in the same folder. So if we go to PC, H with 19.1, copy it. One thing you notice here is the file type's different. You have to make sure to File, Save As, and then when you save it, you want to save it as a CSV. So let's do that again. Save as comma separated values format. So we'll delete this one. Now, here you put the CSV file, so PS underscore H underscore with 19.1, and then end in .csv. Make sure it's the exact same. If you're unsure, copy and paste the file name and make sure. Now here's the columns for confirmation, as we discussed earlier. So let's say we want to see just the neutral loss of both fatty acid chains and the head group. So that would be 2, 3, 4, 5, and 6. So I'm going to put 4:5:6. All of those have to be confirmed. And now for run data dependent on that, true. AIF, which is still beta, we can still put as true. By class, it's false because we're using the fatty acyl chains for identification. It's positive mode, M plus H. And then we could put whatever notes we want over here. And that's it. And then you would run LipidMatch, and it would automatically add this library and search your data for this PCs with 19:1. Thank you. Looking